Hello and welcome back to FPGA PS channel. This training focuses on utilizing the PL fabric resources on the ZCU104 and excluding the Zinc MPSoC block. The design leverages the clocking resources on the ZCU104 to generate two clocks with different frequencies, 100 MHz and 200 MHz, using the Clocking Wizard IP block. To confirm the functionality of the generated clocks, we utilize the provided I/O and control features on the board. The design blinks two PL LEDs at different frequencies. Additionally, we review the various steps involved in bitstream generation in Vivado and study the implemented clocking structure. Finally, after downloading the bitstream to device, the PL LEDs on the carrier board will blink at different frequencies, and reset is controlled by CPU reset push button. Clocking on the ZCU104. The ZCU104 board offers multiple clock sources to meet the diverse requirements of FPGA and processing system applications. These include system clocks, programmable clocks, and user clocks. The IDT chipset, highlighted on the slide, is a one-time programmable clock source. It allows for frequency adjustments via the I2C bus, providing flexibility in clock management. The table on the slide lists various clock sources and their frequencies that provided on the carrier board. For example, HDMI clock, 156 MHz, USB 3 clock, 26 MHz, processing system clock, 33 MHz, user clock, 300 MHz. For this training, we are going to use 300 MHz clock. You can find provided schematic for IDT chipset in this figure. The differential pins of this clock are connected to pins AH17 and AH18 of MPSoC I/O pins. Controlling and I/O interfaces. The ZCU104 board provides different controlling and I/O interfaces. These controlling I/O interfaces are used for quick change of current mode or display the current status without any extra hardware. The first one is the user LEDs. The board has 4 user LEDs, each located near a push button. In our design, we will have 2 blinking LEDs, that after downloading the bitstream, they will start to blink with different frequencies. And it shows the generated clocks, and everything is running properly in the PL side. We also use the CPU reset push button to reset the clock resources. If this push button is pressed, both LEDs will stop blinking. Block diagram of design. The system receives a 300 MHz clock signal from the board. The clock signal is fed into the Clocking Wizard block. The Clocking Wizard is configured to generate 2 clock signals at different frequencies, one at 100 MHz and another at 200 MHz. These clock signals are used to drive 2 27-bit counters. The 27-bit counter counts the clock pulses. It increments its value with each clock pulse. The counter's output is a binary number that represents the count of clock pulses. Slice blocks are used to extract specific bits from the counter's output. The extracted bits from the slice blocks are used to control the LEDs. When the extracted bit is high, the corresponding LED turns on. When the bit is low, the LED turns off. The frequency at which an LED blinks is determined by the bit extracted from the counter. Because the input frequency of second counter is double than the first counter, then the second LED will blink 2 times faster than the first one. Control mechanism. The reset CPU push button is used to control the Clocking Wizard reset. When this push button is pressed, Clocking Wizard reset the frequencies, and counters and LEDs will be stopped. Clock Wizard IP block. The Clocking Wizard is available to assist in utilizing MMCMs and PLLs to create clock networks in ultra-scale architecture designs. The graphic user interface is used to collect clock network parameters. The Clocking Wizard chooses the appropriate clock management tiles resource and optimally configures the clock management tiles and associated clock routing resources. Key features and benefits. It accepts up to 2 input clocks and up to 7 output clocks per clock network. Automatically chooses the correct clocking primitive for a selected device and configures the clocking primitive based on user-selected clocking features. Calculates VCO frequency for primitives with an oscillator and provides multiply and divide values based on input and output frequency requirements. Implements an overall configuration that supports phase shift and duty cycle requirements. Optionally buffers clock signals. Steps to create the Vivado design. Create a new project. Create a new project with ZCU104 and create a new block design for it. Add programmable differential clock, 300 MHz. From the board tab list, add a programmable differential clock. This will add a clock wizard with a differential input and connect it to the appropriate external pins. Add reset. From the board tab list, add a reset and connect it to the reset pin of the Clocking Wizard. Note that when using the board examples, the board file's pre-setups are automatically used. For example, based on the board pre-setups, the differential input is connected to I/O pins AH17 and AH18, which are connected to the 300 MHz clock, and the reset input is connected to the M11 I/O pin, which is the CPU reset push button. Configure the Clocking Wizard. Double-click on the Clocking Wizard to open it. The Clocking Wizard setup will instantiate an MMCM block to fulfill the frequency synthesis requirements. Set output frequencies. Go to the Output tab and add 2 frequencies with values of 100 MHz and 200 MHz. Allow the Clocking Wizard to add the buffers for routing the clocks into the clock network. Review MMCM setup. The MMCM setup tab shows automated selected setups for frequency synthesis. For example, to generate a 100 MHz clock, the input clock is divided by 12 and then multiplied by 4. Add counters and slices. Add 2 counters and change them to 27 bits. Connect the clock of each counter to the Clocking Wizard's outputs. Add 2 slice blocks to make the last bit of the counters as output. Make the slices outputs external pins. Validate and wrap up. Validate the design and add the top wrapper. Synthesis the design and assign the pins. Run synthesis design and wait until the synthesis is finished. Open Synthesize Design and open I/O planning window. As you can see in the I/O port window, the clock input pins and reset pin are already selected properly because we used the board examples. Connect the slice output pins to D5 and D6, respectively. Save the project. At this point, the Vivado will ask you to save your pin setup as a constraint file. Now, you can go to the final step and generate the bitstream. Frequency synthesis and clock distribution. Steps to provide required clocks in the design. Provide the source clock. Ring the source clock through the clock-capable pins. Convert differential input to the single-ended output. This is done by instantiating differential signaling input buffer. Frequency synthesis. Generate new clocks by multiplying and dividing the input clock. This is the MMCM duty. Route the clock through the clocking network. Distribute the clock signal to all parts of the chip with equal propagation delays using the specific network provided by the FPGA fabric. Clock buffer is the key element for clock distribution over the clock network. Open the synthesized design and after that, open the schematic. As we explained before, Clocking Wizard assists in utilizing MMCM, clock management, utilizing proper resources and buffer the clock signals. Here's the list of automated jobs that Clocking Wizard fulfilled based on the selected user setup. Instantiate differential input buffer to convert differential input to single-ended output. Instantiate MMCM primitive. Set up the proper generic parameters for that based on selected output clocks. Route the two output clock signals through the clock buffers to route the clock signal over the clocking network. All of these jobs are easily done by Clocking Wizard graphic user interface. Please note that differential signaling input buffer, MMCM, and clock buffer are primitive blocks, and you need to instantiate them in VHDL or Verilog in order to utilize them in your design. Frequency synthesis and clock distribution elements. Global clock GC pins. Clock-capable pins in ultra-scale devices are specialized pins designed to handle clock signals efficiently. Each I/O bank contains global clock input pins to bring user clocks onto the device clock management and routing resources. These pins have dedicated routing paths to the FPGA's clocking resources, ensuring minimal delay and skew. This is crucial for maintaining the integrity of the clock signal across the FPGA. These pins drive clock signals to the clock management tiles that contains mixed-mode clock manager. The Mixed Mode Clock Manager, MMCM, in ultra-scale FPGAs is a highly flexible and configurable clocking resource used for generating, manipulating, and distributing clock signals within the FPGA. It provides capabilities such as frequency synthesis, phase shifting, and jitter filtering, making it essential for precise timing and synchronization in high-performance designs. Key features of the MMCM in ultra-scale include frequency synthesis. The MMCM can generate a wide range of output clock frequencies by multiplying and dividing an input clock. This allows designers to tailor the clock frequency to specific needs. Phase shifting. It allows precise control over the phase of the output clock signals, which is critical for timing alignment in multi-clock domain designs. Jitter filtering. The MMCM helps reduce clock jitter, improving the stability and accuracy of the clock signals. Multiple outputs. The MMCM can produce multiple clock outputs, each with independently configurable frequency and phase, enabling the design to manage different clocking requirements within the FPGA. Clock buffers. Clock buffers in an FPGA play a crucial role in routing and distributing clock signals throughout the device. To distribute a clock signal to all parts of a chip with equal propagation delays, we must use specific network that is provided with FPGA fabric. Global clocks are a dedicated network of interconnects specifically designed to reach all clock inputs to the various resources in a device. These networks are designed to have low skew and low duty cycle distortion, low power, and improved jitter tolerance. They are also designed to support very high-frequency signals. Non-clock resources, such as local routing, are not recommended when designing for clock functions. Clock buffer directly route the clock signal into global clock network. In FPGA design, when you want to use a clock signal that originates from the PCB and enters the FPGA through an I/O pin, it is common practice to route the clock signal through a clock buffer before using it internally within the FPGA. Now, let's download the bitstream into the device over the USB-J tag. We should be able to see two LEDs are blinking with different frequencies. We should also be able to reset the clock wizard by pressing CPU reset push button. When the CPU reset is pressed, the clocking wizard is also reset. As long as the push button is held down, the clocking wizard remains in the reset state, preventing any output clocks from being generated, which causes the LEDs to stop blinking. Once the reset is released, the clocking wizard resumes clock generation and the LEDs continue blinking.